Okay, so now let's look at the thermal energy of a system and try to understand this quantity better, right? So in general, the energy of any system is the kinetic energy plus the potential energy. For ideal gases, the ones that we are studying here, and a monoatomic gas as this one here, the potential energy would be zero because these particles don't attract or repel each other, so there's no potential energy. So it's all kinetic energy, and if it is a monoatomic gas as opposed to a diatomic gas, then it's all translational kinetic energy. So this here would be, for instance, helium, neon, argon, gases like that are monoatomic gases, which are the energy of a gas is just all translational kinetic energy. So the atoms in a monoatomic gas have no molecular bonds, so therefore this term here is zero. So now what is the energy then of this system? Well, the energy is just the sum of the kinetic energy of all the particles. So the thermal energy is equal to the sum of the energy of particle 1 plus 2 plus 3 plus 4 and so on. And this is just the kinetic energy. And this is also equal to the number of particles times the average energy of each particle. And since the average energy of a single atom in an ideal gas, we found out that is 3 half kT, the total energy then is n times that, right? So it's therefore 3 half n kVt or 3 half nRT. So this is the energy of a monoatomic gas. Okay, so now if the temperature changes, say the temperature goes from some value, let's say the temperature goes from some value T1 to a different value T2, right? Let's assume the temperature changes like that. So then the change in temperature is then 3 half nR T2 minus T1, right? Delta T. So, and this is all the change in energy for the gas. So delta E thermal only depends on the temperature. Now, we've seen that this is also equal to NCV delta T, right? So therefore, we can relate these two quantities here and we say, well, CV then is what is 3 half of R. And this is something that we can get from our theory. And if we go and do experiments and measure the specific heat of say argon, we're going to find that it has just this value. And this is a remarkable experimental fact. Uh, the the energy of a gas is related to the degrees of freedom. What is a degrees of freedom? For instance, a single particle has 3 degrees of freedom, X, Y, and Z. Now, that's a monoatomic particle. Now, a diatomic particle have 3 degrees of freedom, X, Y, and Z, plus 2 rotational degrees of freedom. So it has 5 degrees of freedom. So atoms in a monoatomic gas carry energy exclusively as kinetic energy, 3 degrees of freedom. So they may have more additional mode of energy, for instance, potential energy, but uh, and rotational energy. So this rotational energy is the extra degrees of freedom in a diatomic gas. So degrees of freedom are just the number of distinct and independent modes of energy storage. For the thermal energy of a system of particles is divided among all the possible degrees of freedom. For a system of n particles at temperature T, the energy stored in each mode is 1 half kT, 1 half n kT, or 1 half nRT. So, and this is called the equipartition theorem. But from this video, what I want you to get, I guess the most important idea is that the change in thermal energy is equal to 3 half for a monoatomic gas kV delta T or 3/2 and R delta T. So those delta E thermal. That's the most important idea that we need to get from this video. Thank you.